Okay, welcome to Precalculus. This is the high dive unit with Mr. Sladkey. We're going to explore the relationship between the circle and the sine wave using the tides. Okay, here's our question. An ocean shell seeker knows when the tides are occurring. She uses a formula h equals 30 sine of 28t, where h is the height from the average tide level and t is the time in hours starting at midnight. She finds that the best place to find shells is when the tide is exactly at 10 feet above the average tide line. Since she can't see the shells while it's dark outside, she's trying to figure out when to plan her shell outing. Can you help her? All right. So let's kind of think through the question. All right, I have my beach picture here. Okay, so the tides go in, the tide is in, and the tide goes out. Okay, so that's what we're measuring, the tides in and out, and it actually makes a sine wave when we measure this. And let me just kind of put this as an example. Let's say that this is the average spot, the average line. And maybe the tide goes up to here and then back down to here. Okay, so we have, this is like our 3 o'clock position. And then it goes up to its max position, like 12 o'clock. And then it goes back to our 9 o'clock position, back to the midline. And then to our low position, like our 6 o'clock position. And then back up to our 3 o'clock position. And so the tide is finished. So that kind of shows what's happening. And right here, this distance from the midline to the max point is called the amplitude. Or you could say the distance from the midline to the min point is the amplitude. So the distance from the average tide line up to its max point is our amplitude. All right, and don't forget the period of the graph is from 1 my battery's getting low. So the period, remember, is from when we go 1 full tide. So goes up, back to the middle, down, and back to the middle. That's 1 full tide. That's 1 period. So we need to find out what those two things are, the amplitude and the period. Well, let's make a graph. And you should have a piece of paper out and your calculator, your graphing calculator, while you're watching this. If you would make a graph just like this, on the x-axis we have our time, and I put it in time of 3 hours. Every 3 hours I put a line, and remember that this is time 0, which is midnight. So the time since midnight, hours since midnight. So I made 1 full day basically. And then on the y-axis, we're just going to go feet from the average tide level. All right, so how many feet did it go above average tide or below average tide? Okay, so make this graph and then find these two things. So pause the video and find the amplitude and the period of this function. Don't graph it using a graphing calculator yet. Okay, so you're back. Maybe you gave it a try. Let's take a look at how you'd find both those. The amplitude, well, the amplitude is simply dealing with our radius. It's our radius of the Ferris wheel. In this case, it's 30 feet. And it's the change from the average tide up or down. And then we're going to go up or down 30 feet from that midline. We call that the midline. The period's a little bit harder. We're kind of going to go reverse of what we've been doing. Remember, we've named this as the angular speed. Okay, so we now are going to go backwards. We're going to take 360 degrees divided by the angular speed is the period of the graph, or 12.86 hours. So one revolution of the Ferris wheel, or one tide, one full tide, tide coming in, tide going out, and back to midline, is 12.86 hours. All right, so that's what we're talking about there. All right, so use that information to plot our graph. All right, we're going to actually do the graphing calculator in a second, but use this to plot our graph. So I'm going to put the circle right next to our graph and kind of walk through this. I'll do a couple points and then you can do the rest. We said that 12.86 hours is the period. Okay, we're going to need that number quite a bit. All right, so first of all, at time 0, and we're going to say, like our Ferris wheel example, at time 0, we're at 3 o'clock position. We are at 0, or midnight, and the height is 0 as well. And let's relate this back to the Ferris wheel. Usually we said plus some number, like 65 feet, remember? And that was meaning that the Ferris wheel is 65 feet off the ground. Well, now it's plus 0. There's nothing, so therefore it doesn't even come off the ground. And so we have our Ferris wheel. If we're thinking of the Ferris wheel, it's like dug down, and it's at ground level. In the tide, this is the midline is at 0. All right. So we take, and we need to go to its highest point, which is a quarter of the way. A quarter of the way would be 1/4 of 12.86. So I'm taking my calculator, 12.86 divided by 4, and I get 3.215. So at this point, the amount of time that has elapsed is 3.215. Now, that means that it's at its highest point after that much time has elapsed. Okay, remember we were here at time 0 and height 0. And so we're up there. So it's going to look like this. Okay, let's do our next one. Okay, that would be at a halfway around. Halfway around gets us back to midline, or the average tide. Okay, so I have to figure out how much time that is. Well, 12.86 divided by 2, so 6.43. So 6.43 is like right here. Okay, so there we go. Now I want you to continue doing this problem. So pause the video. Okay, so after you plotted these points, here's how it looks. We have points every 3.21 hours is what I end up having, and so it does our sine wave, and we have 2 periods graphed here, one at 12.86 hours, and then double 12.86 hours is 25.72 hours, and so we're done with 2 periods. Here's the beginning, end of one period, end of another period. Okay, and our question, let's go back to our question and just refresh our memories. They have this formula, and 10 feet above, exactly 10 feet. So that's what we want to know. And not when it's dark. Okay, so only 10 feet above when it's light. Okay, so let's take a peek at this. So really, if I move this up to 10 feet, this is midnight, so this is like in the middle of the night. This is like at 6 o'clock. We're not sure how light it is then. And so really our ideal times are going to be right here and right here. Okay, so we need to find the intersection of those. So this would be tough without a graph. So let's do this. Let's have you pause in a second and take your graphing calculator out and put all of these things into your graphing calculator. You need to put this equation, you need to put this in the x, min and max, and this in the y, min and max. And let me tell you what my window was. I think I went from 0 to 28 and negative 40 to 40. I went by 4 in the hours, and I went by 10 feet increments. Okay, go ahead and do that in your calculator. All right. So let's graph that. And notice I put y equals 10. I put that because then we have the sine wave, and then we have y equals 10. We'll just figure out when they intersect. All right, so here's the graph. I'm going to put this red line up at 10 feet. Looks like that. Okay, and again, I'm looking for that point and that point. So remember, all we have to do for that is to type in our calculator. Well, you already have that in your calculator. And now go to the intersect feature, which is at second trace. Second trace, remember, your spider will be like this, and then it will move down to this, and then you guess. Okay? Do those things, and you should come up with an answer that looks like this. 13.56 hours from midnight up at 10 feet. That's our intersection, and 18.59 hours up at 10 feet. So those are the two perfect times for getting shells. So she wants to know what time that is. Let's put that in actual time. I'm taking my calculator. 0.56 hours times 60 minutes gives us 33.6. So this time, well, 12 hours would be 12 hours since midnight. So that's like noon right here. So 13 would be like 1 o'clock, 1, and then the 0.56 we said is 33.6. I'll just say 34 p.m. Okay, so 1:34 p.m. would be the ideal time at 10 foot from average line. And then the other one, 18 minus 12 is 6, so 6. And then 0.59. 0.59, I'm doing my calculator, times 60 is 35.4. So I'm going to say 35 minutes. So 6:35 p.m. would be our other ideal time for this. Okay, so we answered the question. Let's take a look at another way to solve that problem. You can actually solve this using the circle as well. Now notice I have my triangle. Here's at 10 feet. Here's the midline at 0. Oops. Okay, so we're at 0 and up 10 feet, and similar to the fence problem, I got 10 and I know my hypotenuse is 30, my radius is 30. So all I need to do is take sine of that angle is equal to 10 over 30. My 10 didn't turn out too good. Okay, and then find that angle. All right, that'll give me some information that I can use. I'll show you it in the next slide. Okay, so I solved that out, and I came up with 19.47 degrees. So that angle is 19.47. Now, if I take 19.47 divide by the angular speed, I get 0.7 hours. Okay, 0.7 hours is the time it takes for the tide to go from midline to 10 feet. Okay? And So now what I need to do, I need to figure out where we are at the midline. Well, we know that the time it takes all the way around, because we're going to go all the way around, will be 12.86 hours. Okay, sorry about that. We have to go all the way around. So I'm just going to show you in this. We have to go all the way around. Here's midnight, and we're going all the way around. And then we go that much more. Okay, so we need to have that is one full period. And then we need to add the 0.7 hours to get all the way back up to 10 feet. I mean, we were at 10 feet a couple times, but that was in the middle of the night. So now we want to know in the afternoon. So we simply take 12.86, that's one period, plus our 0.7, and we get 13.56, which is what we said, 1:34 p.m. And then the tougher one is the next time it gets to be 10 feet. Okay, and here's what I did to solve that out. Okay, I was going to erase this, but that's cool. Okay, so, but it erased half my graph. Okay, we got that. We know it takes 0.7 hours for this. And we also know that that's 0.7 hours as well. Okay, so if we could just go like this, we could say we are all the way around, that's one full period, and then we keep going, that's 1.5 periods. 1.5 periods, but we take away the 0.7. So that's what I did. I took 1.5 periods, that's 1.5 times 12.86 is 19.29, but I took away the 0.7 to get 18.59, which is 6:35 p.m. is our other answer. So we solved it with the circle, and we solved it with the graphing calculator and graphs. Okay, I got to tell you a couple. I got to ask you a question. Why did the cookie go to the hospital? Because he was feeling crummy. Second, I have another one for you. Okay, Sven had just fixed his car blinker. So he's in the driver's seat. He asked Oli to check to see if it was working. So Oli goes back to the back of the car, checks to see if it's working, and Oli actually goes to the front of the car. And he tells Sven, yes, no, yes, no, yes, no. I thought that was a funny one. Okay, you're going to have a sandcastle question tonight for homework. Actually, you're going to work it in class tomorrow. And similar, you can see somewhat similar to what we just talked about. You can use class time to work all of that out. Okay, I want to go through a couple more problems with you, that exact value problems, just to review and refresh your memories. Some of you guys got this down, no problem. Initial side, and then we go terminal side. We know that this is 150. We know that this is 30. Okay, we draw our reference triangle. I often explode the reference triangle to kind of see it better. Some of you have been using 1 here. Some of you have been using 2. Doesn't matter either way. I'm going to use 2 this time. 2, and remember, the side opposite 30 is our half, so that would be half of the hypotenuse. And then we have 1 radical 3, but it's negative because it went left. Just to refresh your memory with that, if you go left, you have to be negative. If you go up, it's going to be positive. Okay? So cosine is going to be negative square root of 3 over 2. Okay, let's do another one. Sine of 210. Sine of 210, initial side, 210. Draw our reference triangle in. Okay, again, this is 30. 210 minus 180 is 30. So we have our triangle, 30. I'm going to put this as 1. Excuse me, opposite 30 is 1/2. However, we went down there, so we have to have negative. And this one's negative half square root of 3, or negative square root of 3 over 2. Okay, and it asks for sine, so that's opposite over hypotenuse. So sine of 210 is negative half. Okay, tangent of 300. Let's do that one. 300, initial side, 300 would be like this. We're left with, that was a bad triangle. We're left with the triangle looks like this. 60, 30. I'll make this 2. We went to the right. Remember, if you go to the right, it's positive. So that's opposite 30. That's 1. If you go down, it's negative square root of 3 over 2. Okay, well, tangent is opposite over adjacent, or y over x. So tangent of 300 is negative square root of 3 over 2. All over 1. I messed that up. You were wondering, weren't you? This is simply negative square root of 3. Sorry about that. Okay, so tangent of 300 is opposite over adjacent. So negative square root of 3 is our answer. Okay, I want to talk about quadrantal angles. Okay, let's talk about quadrantal angles. Remember, we've said quadrantal angles are angles that are at any multiple of 90. Okay, so here, 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 remember at when it's at its max or min, or at the midline. Okay, so 0, 90, 180, 270, and so on. That's a quadrantal angle. Okay, so you should also have these memorized. We've talked about this quite a few times. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So those should memorize, and let's talk about okay, let's do a couple problems with quadrantals. Okay, find the exact value of 180. Unlike the regular exact value problems, quadrantals, we can't make a triangle. You know, because you have your initial side and your terminal side, there's no triangle that's formed. You know, if you do, you try and you kind of imagine you can't do it. However, what you should do is mark out the point sign or at 180. So initial side, our terminal side at our circle, we just need to think through what the coordinates of that point are. Okay, and we're going to use the unit circle. So I'm going to say -1, 0. So my x value is -1. My y value is 0. And my r value in any unit circle is 1. Okay, so remembering these things, and I'm going to split screen it. Remembering these things, that if we have sine of theta, it's y over r. Okay, so y over r would be 0 over 1, or 0. Cosine is x over r. Well, that's negative 1 over 1, which is negative 1. If we go to tangent, tangent is y over x. Y is 0 over x, which is negative 1, which is 0. So tangent of 180 is 0. Okay, cosecant is just the reciprocal of sine, but that's 1 over 0. It's undefined there. Secant is the reciprocal of cosine, so it's negative 1. It's 1 over negative 1, which is negative 1. Still, cotangent is the reciprocal of tangent, so it's negative 1 over 0, which is also undefined. Okay, so those are the rules that will help us with quadrantals. And lastly, let's do this. Let's do the 270. Okay, I'm going to go back to regular screen. Okay, so try this one on your own. Graph 270, mark x, y, and r, and then see if you can get these values. Okay, so let's check your answers. When we have sine of 270, here's all the 6 trig functions, and here's your answers. Hopefully you did those right, and I appreciate you watching. We'll have homework that we'll do in class tomorrow, and have a great day. Thanks for watching.